Hello, my name is Matías Toro, and I'm going to present Abstracting Gradual References. This is a joint work with Eric Tanter. Gradual typing supports the smooth transition between static and dynamic checking based on the programmer-controlled precision of type annotations. Gradual typing is about type precision, wherein precision is mostly introduced using the unknown type, which may represent any type whatsoever. For instance, unknown is more imprecise than int, and also more imprecise than unknown, arrow unknown, and that is more imprecise than int arrow unknown, etc. Notice that the direction of the ordering characterizes imprecision, so the unknown type is always the most imprecise type. Precision helps us derive consistency relations, such as consistency, which is the gradual counterpart of equality. For instance, int is consistent with unknown, but not consistent with bool or with unknown arrow int, for instance. So this work is about gradual references, and since the first paper on gradual typing on 2006, references proved to be tricky. The first design of gradual references was simple but very restrictive, and in later years, several papers on gradual typing has been published, and among those there were various designs of gradual references motivated by factors such as efficiency or expressiveness. So first we'll do a quick recall, LML, of the essence of any mutable data structure. Mutable references are a form of computational effects that provides an assignment operation that changes the content of a value in a store or heap. Lambda ref, the simple-type lambda calculus extended with mutable references, add three basic operations on reference. Allocation, which allows to create new references, returning a new location or pointer. In this case, we are creating a new location that points to the number 4. And notice that the reference has type ref int, meaning that the content of the reference value is an int. We also have the dereference operations, which allows to read the reference value of a location. Here we are reading 4 from reference x. An assignment, which allows to update reference values. Here we are updating the content of the cell to 10. So this program will read 10 from the cell. Among the different design decisions of gradual references, we review the 4 major. The first one, presented in the first paper of gradual typing, which we call invariant references, imposes that reference type has to be invariant with respect to consistency. For instance, consider this program, where we are allocating a reference with content 4. This program type checks, but as refint is consistent, because refint is consistent with refint. But if we change the type of y to ref unknown, then the program no longer type checks, as refint is not consistent with ref unknown. The second design of gradual reference is called guarded references, which is a space-efficient approach to gradual typing based on coercion. Here, the type system allows consistency variance for reference types. So for instance, if we consider the same program, now it type checks, but if we change the type of x to ref unknown and the type of y to ref bool, for instance, and read from the location later, then although the program still type checks because ref bool is consistent with ref unknown, the program will fail before the dereference, as we are expecting a bool but the content value is an integer. We can fix this program by inserting an assignment to some boolean before reading from variable y. The third approach is called monotonic references, and this design is motivated to avoid doing unnecessary checks on statically typed references. To do that, the type of heap cell might vary only towards more precise types, and this is done by performing casts of references directly on the heap. So for instance, the same program as before, the cast of x to ref bool will be propagated to the heap, producing a runtime error because the content of the cell at that moment is an integer. If we change ref bool to ref int and update the content of x to true, the cast now is going to succeed, but this program will still fail at runtime because at line 2, x is going to be refined to a reference of int. Finally, the fourth approach is called permissive reference, and its main goal is to achieve flexibility instead of efficiency. So when using permissive references annotated with a star, the program is translated to a different one where the type of all heap cells are treated as unknown. These four developments reflect different design decisions with respect to Gradual references, such as, is the reference type constructor variant under consistency? Can the programmer specify a precise bound on the type of a reference and its cell? Can the heap cell type evolve with precision at runtime, and how? Of course, there is no correct answer to this question, but we try to answer them for a Gradual language derived with a systematic methodology. In particular, we consider the abstracting Gradual typing methodology, or AGT, as it naturally scales to auxiliary types such as mutable heaps. AGT helps to systematically derive a Gradual language from a static language using abstract interpretation at the type level. And it has been shown to be effective in many contexts, such as soft typing, refinement, effects, union, liquid inference, security typing, dependent type, parametricity, and program verification. As you can see at Jenna Weiss talk, these two stay on UPSLA. Specifically, we apply AGT to lambda ref, the simple type lambda calculus with references, to obtain lambda ref hat. This is the first application of AGT that focuses on references, where we also show how to apply the methodology step by step, including the dynamic semantics. For the derived language, we prove properties such as type safety and the Gradual guarantees, and we present the first formal statement and proof of the conservative extension of the dynamic semantics of the static language for a Gradual language derived with AGT. We answer the questions about which semantic follows from applying AGT, and if it justifies one of the existing approaches. We prove that the derived language corresponds to the semantics of guarded references from Herman et al. Using bisimulation. But we observe that both languages differ in the order of combination of runtime checks. As a result, guarded references are space efficient, whereas lambda ref hat is not. And this has nothing to do with references. Nevertheless, we present changes needed in the dynamic semantics to achieve space efficiency, technique independent from mutable references, and therefore applicable to other Gradual languages derived with AGT. We also answer if we can recover other variants of Gradual references by presenting lambda ref hat PM, an extension with support for both permissive and monotonic references. And finally, we prove for the first time the non-trivial theorem that monotonic references satisfy the dynamic Gradual guarantee. To apply AGT, we start from a static language, in this case lambda ref, with the meaning of Gradual types, where we define the syntax and interpretation of Gradual types. So for instance, the meaning of the function from int to unknown is the set of function from int to t, where t can be any type. And we also have to provide the meaning of evidence to raise errors when type inconsistencies are detected. So to explain this, consider this program where we have the successor function applied to false. This program type checks as both subterms are ascribed to unknown. To detect type inconsistencies at runtime, the program is augmented with two evidences to justify why consistent judgments hold in its type derivation. Here, evidence epsilon1 justifies that the type of sux, which is int or int, is consistent with unknown. And similarly, epsilon2 justifies that bool is consistent with the type of the ascription, unknown. At runtime, before the application happens, we try to see if we can justify the transitive judgment. As expected, combining both evidences using transitivity is not possible, so a runtime error is raised. From these three components using AGT, we systematically derive lambda ref hat. More in detail, from the type system of lambda ref and the meaning of Gradual types, we derive the static semantics of lambda ref hat. And from the type safety proof of lambda ref and the meaning of evidence, AGT provides a direct dynamic semantics defined over Gradual typing derivations augmented with evidence. So to formalize this approach, we elaborate lambda ref hat terms to intrinsic terms, which are a flat notation isomorphic to typing derivations. This intrinsic language is called lambda ref hat epsilon. To define the meaning of Gradual types, first we define the syntax of Gradual types. So here we have Boolean integers, function, references, and the unknown type. Then we give them meaning by defining a concretization function from Gradual types to set of static types. So for instance, here, the meaning of booleans is just the singleton boolean. The meaning of a ref g is just a set of ref t, where t is in the meaning of g, and the meaning of unknown is it can be any type whatsoever. So then we define an abstraction function from set of static type to gradual types, forming a Galois connection. Then we have to do the same for evidence. Here we're using the same interpretation. And by using the IGT methodology, we get some nice properties by constructions, such as type safety, meaning that well-typed programs do not get stuck, the static and the dynamic gradual guarantee, meaning that typing and reduction are monotone with respect to imprecision, and the conservative extension of the static discipline with respect to lambda ref, and the embedding of the dynamic discipline with respect to the untyped lambda calculus with references. Regarding the conservative extension of the static discipline, we prove for the first time, for a language derived with AGT, that the dynamic semantics of a gradual language and its static counterpart are equivalent for static terms. So starting from a well-typed term for lambda ref and its elaboration to an intrinsic term, then if one term terminates, the other as well, and the resulting values and stores are related using a logical relation. We also answer if AGT justify one of the existing approaches, and we show that it corresponds to guarded references of Herman et al. To do that, starting from a gradual term T from lambda ref hat and a compilation to HCC+, which is a modern space-efficient version of guarded references, and to the intrinsic semantics of lambda ref hat, we prove that either both terms terminate, reduce to an error, or diverge, establishing a bisimulation between both semantics. As we previously said, lambda ref hat is not space-efficient, as it may accumulate an unbounded number of evidences. For instance, consider the omega term, the self-application of lambda x, where x is applied to x. The first application will wrap omega into an ascription and its evidence. The second application will accumulate to ascription, the third 3, and so on. These evidences will be combined after the subterm is reduced to a value, which is never going to happen because omega is going to diverge. So to address this, we use the same technique used by Herman et al. In guarded references, and we change the dynamic semantics to recover space efficiency, which is a technique independent from mutable references. So now, before reducing omega for the third time, the outermost evidences are combined, preventing the accumulation of casts. As a final contribution, we showed how to extend lambda ref hat to support for permissive and monotonic references by introducing 3 reference constructors to create guarded, monotonic, and permissive references. Here we use the same technique used by Sick et al. In monotonic references. In the dynamic semantics, we use 2 different stores, mu as a regular store and v for evolving stores, which means that there are stores that need to be reduced. So before reducing a term, we must first reduce evolving stores until we get a regular store. For this extension, we present the first proof of the dynamic gradual guarantee for monotonic references. Result not trivial, as it requires careful consideration of updates in the stores. For instance, and informally, the definition of precision between evolving stores is involved. We say that a reference and its content is more imprecise than another if the less imprecise term reduces to some value v1, then the more imprecise term reduces to a more imprecise value. So as a summary, this is the first application of AGT that focuses on references, where we show the methodology step by step. If you look for a tutorial of how apply AGT, look at this paper. We also prove that the runtime semantics are equivalent to lambda ref for static terms. We also show that lambda ref hat correspond to guarded references, that lambda ref hat is not space efficient and how to recover it. And finally, we show how to support for monotonic and permissive references, proving the dynamic gradual guarantee for this extension. Thank you.